All right, hello everyone. Welcome to Physical Geology 1403. I'm going to be recording this, like I just said, for my online students. The way that I like teaching is I make it as interactive and fun as possible. I have a lot of physical examples that I bring around and I show, and I include the camera in those conversations and in those demonstrations as though it was another student to try and improve how included my online students feel. Okay, my online students watch this through a program called GoReact, where they get to pause it and leave notes, upload files, look at files that I upload, look at links that I provide links themselves, leave comments in any way, ask questions, and I go back in and I answer their questions later. Timestamp to the moments in this lecture. And so it kind of all works flawlessly to make kind of a synchronous, asynchronous experience. So if I'm talking to the camera at any point, I'm not insane. Okay? I only talk to inanimate objects when no one else is around. All right? Okay, let's start off with a little bit about who I am. I'm going to be your geology professor, primarily because I'm the only geology professor. You had no other choice but me, so well done. I have had a lot of different experiences in geology. I have a bachelor's degree from Brigham Young University, Idaho, in geology. I have a master's degree in geology from the University of Louisiana at Lafayette, and I am most of the way through, 3 out of 5 years through my PhD in Earth System Science and Policy. My dissertation that I'm currently writing, I finished all the classwork for my PhD, I'm just working on my dissertation now, is lunar resources and how we can develop policies that nations and corporations aren't squabbling over them in the future as we develop them on the moon. Work experience-wise, I've worked in the mining industry, I've worked in paleontology, I've worked in the oil field, I've been in education for the last 6 years now, I've worked in museums, I've kind of been all over. Been to every state in the US except Alabama. Don't ask me, I don't have anything against Alabama. I've never made it. And I lived in Louisiana for 3 years, so I'm kind of ashamed that I never made it. But here we are. I'll get there eventually, and then I can say I have all 50. Been to most of the provinces and territories in Canada, Japan, Germany, Austria, Switzerland, Scotland, Ireland, England, Iceland, Mexico, Belize. Been around a lot. Some of it for fun, some of it for business. But I love this planet. I love everything on this planet. I love the living things on this planet. I have a classroom full of animals here and another room full of animals over there, for those of you that may not have noticed. But also the rocks, the things that makes our world. This is why I love geology. I love learning about our world. And something you'll come to learn about me, I kind of already gave you a clue about it when I mentioned my dissertation subject, but I love taking what we learn about our world and applying it to the rest of the universe. Okay? So I'm going to be bringing up situations like this a lot. Like, okay, this concept, we just learned about this concept. Who thinks it's cool? Great! What if I told you it's true on Mars? What if I told you it's true on this planet 40 million light years away? Physics is physics, laws are laws. Okay? So when you learn things in my class, you're not just learning about Earth. I'm teaching you about the things that happen on Earth so you understand the universe better. Okay? All right. Oh, yeah. This is my family. This is the most recent family picture we took back in November. It's my lovely wife, Jessica. Branson got to meet her for a second. She was just here visiting before you all walked in. My oldest, Declan, he's 8 years old. My middle child, Isla, she is 6 almost. She'll be 6 in November. And then Liam just turned 4 a few weeks ago. And he just started school this week. And the first day went real good. Second day of drop-off went a little harder. But he'll get over it. He'll be fine. Okay. That's me. Any questions about me or things I've done or anything I've said? No? All right, well then let me tell you something else about me. Oh, here, let me have that pen.
Oh, real weird.
Yeah, that was fine. Luckily, if I miss it, I don't have to go far for it, right? Questions are essential in my class. This is a science class, okay? And science is useless without the question. There would not be science without questions, because the entire point of science is to ask questions. When I say that, a lot of people are like, well, isn't the whole point of science to find answers? I would say no. I would say no. You can find all the answers you want in the world without science. You go on Instagram or Facebook or TikTok, and you'll find a billion people who think they have answers. They don't use science to do it. Science is about asking questions. Because it's in asking the questions that you demonstrate a desire to know, not just, I don't know, want someone to spit something at you that you think is good enough. You know? So, ask questions, please. If you're not asking questions, I don't know if you're listening to what I'm saying. If you're not asking questions, I have to assume you may not understand what I'm saying, right? And I know that the inclination is, well, I don't want to look like the dummy, right? Everyone else must get this because they're not asking questions, but I have a question, but I'm not going to say it because no one else is asking. I guarantee you, if you have a question about something in my class, at least one other person in this classroom will be grateful that you asked it, okay? There are no dumb questions. I really mean that, all right? Okay, so please ask anything at any time. Relevant questions would be welcome. Irrelevant questions can still be fun. All right, so now we're going to go around the room and we're going to talk about each of you. I would love to know, I would love for you to introduce yourselves, okay? I want to know what your major is. I want to know where you're from and one cool thing about you. And then for my online students, feel free to pause the video here and do the same thing with each other, okay? And I'll go back and look through those here in a bit when I upload this for y'all. We're going to start over here with Kate.
My name is Kate. I'm originally from Laredo, Texas, and some people about this that I've been to Disney twice.
Disneyland or Disney World or both?
Well, I've been to Disneyland twice and Disney once, and I'm currently going to go on a cruise. It's free.
A Disney cruise? Disney fan. Okay. Okay. I went on my first cruise 2 years ago. I went to Alaska. Loved it so much. I went on another cruise earlier this summer to the Caribbean. I like it. Hold on. Huh?
We're going to the Bahamas.
The Bahamas. Nice. Nice. I think, I don't know, maybe it's because I'm a geologist. I prefer Alaska. The mountains and the fjords and the glaciers and everything. I actually got to spend a whole day up on a glacier. It's fantastic. It's just more that appeals to me as a geologist, the things that interest me. But it's a lot of fun. It's weird. Yeah.
Hi, my name is Annabelle. Sorry, what was the question?
What's your major?
Oh,
Did you say your major?
Oh no, I'm taking business administration.
Business administration. Okay. So major, where you from? Some cool about you.
My name is Annabelle. I'm majoring in business, and then I'm from Odessa. And then something cool about me is this past summer I went to Europe.
Where?
I went to I went to London.
London.
Yeah.
Yeah. Okay. UK.
Yeah.
Good stuff. I have been to England. Just the outskirts though. The part next to the northern UK. I've been to northern England. I haven't been to London.
Mm-hmm.
Someday though.
Yeah.
That's fantastic. How long were you there?
I was there for like 2 weeks.
What was the vacation?
Honestly, my aunt had a work trip, so I just went with her. Yes.
Yeah.
Mm-hmm, thank you.
Yeah. And what was your major again?
Business.
Business admin.
Yes, sir.
Okay. All right.
My name is Chloe. My major is business. I'm originally from El Paso. I was born there, wasn't raised, and I moved here with my family. One cool thing about me is I can ride a motorcycle, but I don't know how to drive a car.
Okay. Okay. Are you old enough for a motorcycle license?
I wouldn't say, but
Well, I didn't. You said you know how to ride a motorcycle. You didn't say you rode one
license.
here, so. Okay, I'm gonna pause real quick here. How many of y'all are dual credit students? Just so I can get that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just you two?
No.
Oh no, you are dual credit. That's right. Yes. So you're the only one. Okay. Good to know. I was just telling him when he walked in, he was the first one in, and I was like, "Are you dual credit?" He said, "No." I was like, "Man, they never tell me who the dual credit students are." So I always have to ask on the first day. So this is going to be really easy to remember who is and who isn't. Okay, great. Thank you, Chloe.
My name is Iloni. Who is this?
Yeah, where you're from, what your major is, and some cool fact.
I'm Florence. I'm a major in business and landscaping.
Did you say for business?
Man.
I have the world's leaders in my classroom. Next generation. Okay, great. And then what was your cool fact? Sorry. You like baking? What do you like to bake? Is this something that you just kind of like decided that you like and you started playing with it? Or was your family baking business? Oh, you do? Nice. Good for you. Alright. Did I get the credit? I did get the credit. What was your name?
Mia.
Mia, that's right.
I'm Mia, and my major is business and marketing. And you know the travel.
You like traveling? Okay, where do you travel?
I traveled to California. A lot of places in Texas.
Okay, yeah. Okay. You've probably been more places in Texas than I have. Been here 6 years, and I pretty much just come here, Fort Worth, here, Fort Davis. You know, I don't really. Texas is big. I haven't seen a lot of it yet. I mostly work. Cool. Awesome. And you're from here, you said?
Mhm.
Okay. Well, thank you.
My name is Renee. I'm from Odessa, Texas. My major is business and equals, what is it?
Yeah, some cool about you. Like you have purple hair, for example.
Yeah.
Oh no, that was just an example. You have a strawberry shortcake shirt on. My daughter would be all over you right now. Yeah. Purple hair and a pink strawberry shortcake shirt.
Yeah, I guess it's not
Okay.
My name is Angelina. I'm a business major. I'm just a sugar glider.
You used to have a sugar glider.
Yeah.
Oh, that's so sad. Sugar gliders are cute.
Yeah.
Yeah, it's a good one to have. I like mammals as pets, but they are too much work for me. I'm not gonna have a dog. I'm not gonna have a cat. I thought about getting a chinchilla at one point. I'm not. They're fun to cuddle with, but reptiles are just so much easier. I have everything I've got are reptiles, with the exception of the one frog. Okay. I guess we'll pause here and give some animal introductions real quick. Around my neck, right here, this is Diablo. He's a 3-year-old ball python. I've got Darwin, the green iguana, over here. He is 12 weeks old, currently going through his first shed, which is why he has some weird dead skin on his face. But by the time he reaches a year, he'll be about 3 feet long. When he is full grown, he'll be about 6 feet long. So he will not stay that small for very long. Over here, I've got Petrov, the Russian tortoise. Okay. Over there in that corner, in the foggy container, I have Glinda. She is an Australian tree frog, okay, also known as a white tree frog, also known as a dumpy frog, because they're chunky. She chunky. But yes, her name is Glinda, and for any of you that are Oz fans, you might wonder, wait, why would you name one Glinda without having an alphabet? I did have an alphabet. I'm not going to talk about it. So we're currently I just have one Glinda. And then over here, I've got in that small container by the window 2 rough green tree snakes. That is a local species. They are the big one. If you go over there and look, the big one is Ka, which is the name of the snake in the Jungle Book, right? I name all of my snakes for the most part after villains, of one thing or another. So we've got Diablo, we've got Ka, and then I have a smaller one in there who is an expert at hiding and escaping. He's escaped twice so far. His name is Houdini. Okay. Let me. They're insectivorous. They eat bugs.
Oh.
Absolutely zero threat. Couldn't even bite you if they wanted to. Okay. I heard some panic in this corner. And then in the little pool over there, I've got 3 ornate box turtles. The large one is Gwendolyn, the medium one is Cecily, and the small male is Ernest. Because I am an Oscar Wilde fan, The Importance of Being Earnest is one of my favorite plays, so I named all of them after characters in that. In the next room over, I have another room which we have called the zoo. Most of my animals used to be in there, then it got really crowded, so I put some of them in here. I've got 2 more ball pythons. The yellow one is Medusa, and then the gray one is Basilisk. And then I've got an orange and black Honduran milk snake named Shere Khan, which is the tiger from the Jungle Book, right? And I think that's all I've got in there. Yeah, I used to have a red-eared slider. I let him go over the summer. He's not here anymore. He got too big for me to take care of. But yeah. Native species like the sliders, those tree snakes, these ornate box turtles, when they get too big, or when they recover well enough from whatever reason I rescue them for, I let them go again. So it's temporary for the native species. These exotic species, like what I've got over here and around my neck, I keep those. It's illegal to let them go, and I wouldn't watch them. This guy's from Africa. The ball pythons are from Africa. We've got an Australian frog, or that Russian tortoise is from Afghanistan. The iguana is from Central America, and then the milk snake is from Honduras. So those are all exotic. They can't be let go, and they should be. They want to survive long. Okay, now that we've introduced the animals, back over here.
My name is Carissa. My major is psychology. I'm from Odessa, born and raised. And a cool fact about me is that my lucky number is 8 because my birthday is August 8th, 2008.
Hey, how about that? August 8th, 2008. Let me think. If I think hard enough, I'm pretty sure I'll remember exactly what I was doing that day. 2008 was a big year. Let's see. My anniversary is August 7th, so very significant week for us. Okay.
My name is Branson. I major in engineering.
Okay, we've broken out of the business section. Clearly, over here, we've got this. Not only is this the women's side of the room, it's also the business side of the room for the most part. And then moving over here. All right.
From Monahans.
Monahans.
Yeah, fun facts about Monahans is also August 8th.
Your birthday is also August 8th? Man, if we had started a few weeks early, we could have had a party for you guys. We even have a caterer in the house who could have made a cake. How about that?
My name is Jordan. I major in business.
You can go sit over here if you want.
I'm from Odessa, and something that just got me is I like to play football.
You like to play football. What position?
Center and DN.
I say that like I know what it means. I'm not familiar enough with football. I'll watch the NFL if the Seahawks are playing. I don't have loyalty. Hold on now, I see that face. I don't have loyalty to a team, but my wife is from Seattle, so I am an obligatory Seahawks fan, and therefore we watch those games.
You should be a Cowboys fan.
I should be a Cowboys fan? I'm kind of a passive fan of whatever. Like, if my friends invite me to watch a Cowboys game, I'll be like, yeah, Cowboys! If my friends invite me to a Giants game, I'll be like, yeah, Giants! If my friends invite me to a Red Sox game, I'll politely decline.
We're all in blues also.
Oh, yeah. Soccer, I actually like soccer a little more than I like American football. Any of you guys watch the World Cup? Oh, it's crazy. It's a crazy cup. I'm so happy that Spain beat Argentina's trash. It was very satisfying. All right.
My name is Naeem. I was born and raised in Odessa, and my major is in business administration, and I am looking about because I've been playing soccer all my life.
Soccer? Yeah, okay. Cool. Yeah, so there's a show on Apple TV called Ted Lasso. My wife and I just started a few weeks ago. Have you seen it?
I think so, yeah.
Okay. We're really enjoying it. It's a feel-good show, guys. Like, there's so many depressing shows out there. If you need a feel-good show, Ted Lasso. # not sponsored. Okay? But, I mean, after having watched the World Cup, we wanted to wait to start it until after the World Cup. Because we were like, okay, I don't want to get distracted by mixing soccer signals here. And I'm glad we did. Okay, you like soccer, you've been playing it your whole life. Love it. What position do you play?
I normally play striker, but I think now I play midfielder.
Okay. Took a step back. Okay. Well, there's nothing wrong with that. Midfielders get a lot of play. Okay, good deal.
My name is Gregory. I'm from Odessa, and my business major. My truck's back in the shop.
Your truck is back in the shop?
Oh.
Is that an analogy for something, or do you literally have a truck that's in the shop?
It's living in the
Okay.
shop.
Okay. What kind of truck is it?
It's a 2013 F-250.
Okay. Nice. Big truck. Okay. Nice. And you're from
Odessa.
Odessa. Okay, cool. And your major was
Business.
business. So many business. Yes.
I'm Alec. My business is, like, my major is business. I'm from here, and I used to have a snake, but it died.
Ah, what kind of snake was it?
Ball python.
Ball python. I always recommend if people want to start getting into snakes, you start with ball python. They have a tendency towards being more chill than other species. Every snake has a personality. Diablo, super chill. Medusa stays in her terrarium for the most part. I might bring her out every now and then, but none of the rest of you will hold her because she is super feisty. She will snap at me, and I've had her since she came out of the egg. So she absolutely would snap at someone else. It has. He's never taken a snap at anyone in his life. He's been held by thousands of people. I take him to all of the activities. So, yeah, everyone has a personality, but I always recommend ball pythons for starters because they tend to be the easiest and chillest among snakes. That's cool. That's cool. What do you know what kind of morph it was? No.
No idea.
All right. One thing that we're going to talk about is kind of touch on a little bit in this class, but mostly going to be 1404 content. If you stick with me through fall 2 and you take my 1404 class, we're going to be touching on principles of evolution. And so we're going to be talking about genetics. For those of you that have taken biology, it's going to be very interesting conversations. The reason why there are so many different varieties of snakes, particularly like ball pythons, there's one species, ball python, that has more than 6,000 variations of colors and patterns on it. And every single one of those variations is a result of people choosing which ones to breed together to make different variations. And so over the generations of snakes, it's kind of percolated out to the 6,000 different variations we have. It's fascinating. Genetics. Okay, great. Thank you so much for introducing yourselves. Another moment to ask any questions, if anyone has any.
How big is Medusa?
How big is Medusa? Medusa is that long now. When I got her, she was like here. Fresh out of the egg, that's about how big they are. She's grown to about there. She's a year younger than him. My plan is actually to breed Diablo and Medusa next year. Because she has a recessive trait. It didn't manifest in her, which means that she herself is not a particularly valuable specimen on the snake market. He also has that same recessive trait, but it didn't manifest in him, which made him not very valuable on the snake market. But when you take two individuals that have the same recessive trait, and they don't have any traits that will be dominant over those recessive traits, I told you we were going to do this in 1404, and now I'm doing it now, then that recessive trait has a much higher chance to manifest in at least some of the hatchlings. So if she lays a clutch of, say, a dozen eggs, then one or two of them may have that manifested recessive trait from both parents, which would make an extremely rare snake variant. And that would be very cool to have. Yeah. Those can go for quite a bit of money. I've never spent more than $100 on any snake ever. But there are snakes that go for $7,000 easily, depending on how rare their traits are. So, yeah. Good question. Any others? Love the questions.
What do you feed them? Like, what is it like mice, or do you feed them like dead? Because I know some snakes, like mine doesn't like to go hunting for it. It likes it when it's already dead.
Okay, yeah. It just depends on how they're raised. All of my snakes, well, for the most part, my snakes, I've gotten all of them fresh from the egg, and so I've chosen to give them live prey. I try and keep my animals as close to what their native habitats would be as possible. You'll see that all of them have the heat lamps set to just the right temperature that they would get out in their native habitat. Each of them has a humidifier, the ones that need it, to keep the humidity right where it needs to be. The Australian rainforest, right? A Central American semi-tropical zone. All of these different things, I keep them balanced just right. And so I do the same thing for their food. So for my pythons, I give them live prey. And for my milk snake, I give that also live prey. Although that one tends to upset my wife when I bring it up because my milk snake is still, hey buddy, my milk snake is still small enough that the only thing he can eat is baby mice. So yeah, a little heartbreaking when you put it in there, but you gotta remember it's the circle of life. Yeah, live rats for the pythons. And a live baby mouse for the milk snake. and live crickets for those snakes. Mustard greens, collard greens, squash, things like that for the tortoises and the box turtles and the iguana, and duba roaches and crickets for the frog. And I only have to feed them. I feed the snakes once every 2 weeks, and the tortoises and the iguana and the frog once every couple days. Reptiles are way easier. Slower metabolism, is cold-blooded. All right. Any other questions? Okay. All right. Well, anytime you feel the hankering, feel free to ask. All right. You ready to go say hi to some friends? Hold on. Anyone else that wants to hold them? Chloe, feel free to. His morph is called Fire Leopard. So fire, that's what gives him that popping yellow color. He's actually going to shed here in a week. Probably in about 2 weeks, when I bring him to class again, you'll see that he will have shed, and his yellows are going to be like banana. This could be a bright banana yellow, and with the black markings, it's very striking, okay? So fire, that's the trait that makes the yellows brighter, and leopard, that's what his pattern is. And his recessive trait is called het clown. If you go after class and you look at Medusa in the other room, you're going to see that she has also bright colors, but hers is a variant called pastel. And she has a different pattern from his called hurricane. And she also has that recessive het clown. And so the opportunity when they made together for that het clown to manifest, it's going to split apart either the leopard or the hurricane patterns and make this sort of weird, random, spotted sort of pattern. It's going to keep the yellows from both parents and have orange dots along the side if everything adds up. Yeah. It would be really cool if that happened. Yeah. Okay. Let's start talking about the class. Okay, so clearly this is me. This is my email right here. Please take note of that for a very important reason that I need everyone to remember. I will not be relying on the Blackboard message service. It is inconsistent. It does not always tell me that you sent me something. Oftentimes, a student will send me something, and I won't know that you did until I log into Blackboard to grade something, and I see a little 1 next to the messages thing. I don't get a notification. So please, if you need my attention, which if you're sending me a message, I presume you do, use email instead. It goes straight to me. It goes straight to my phone. It's right away, right? The message service is inconsistent. Try not to use it. Online students, that's the same for you. Come on, lock on. There we go. Same for you. Do not use the Blackboard message service. Please, please, please only use my email. Far more reliable. It says class time is variable. That's because I teach a bunch of different sections simultaneously. For you guys that are here in person, we're going to meet every Tuesday, Thursday, 9:30 to 12:30. Technically 12:20, but you know what I mean. And for the last hour, it's going to be lab time for the most part. Today is going to be an exception. You're not getting a lab today. As our class times progress, lectures will gradually become shorter and lab times will gradually become longer to make sure that you're getting all the work done you need to and you don't feel super stressed about getting a bunch of stuff done in a small amount of time towards the end of the class. Okay? All right. Syllabus is on Blackboard. Please feel free to take a look at that. If you see a mistake on the syllabus, let me know with mercy and grace, please. Because we came back after our summer to find that they had completely revamped the entire syllabus program. And every syllabus that we had before summer was gone, and we had to completely remake everything from scratch. So if there was something I missed, if there's something that clearly should be there, or a section that's partially blank, let me know. There might be a few bugs in the system, or I may have genuinely forgot something. So let me know, and I will fix it as soon as I can. Okay? Are you okay with snakes?
Yeah, we're fine.
Okay. Alright. There are no textbooks that you need to get for this class. The only textbook that would be relevant, I provided for you. You may have noticed on the Blackboard shell, for those of you that have looked at it, there is a link that says class website. If you're not okay with that, we
No, I just want to touch it.
Okay. Have you ever touched a snake?
No.
They're so small. They're so small.
Not slimy.
That's why they're actually.
Here, just one finger. No?
Okay.
Okay. All right. Yeah, I provided a website. I made a website that has all the resources. It has all the lab things on there. It has some Q&As, and it has a textbook free for you to use. I will say that with a caveat here. The textbook is not required because it is supplementary to me. The college hired me as an expert to teach geology. I am the expert giving you the information. That means every other source of information out there in the world is not going to do you as much good as I am. Okay. I don't want you to be uncomfortable, so I'm going to shift him away.
I just want to touch it.
And yeah, we can't.
Sorry, I just want to touch
We
it.
can't let it go under there. Let's have to go this way. You guys okay if it goes this way? You are? Okay, we'll make sure it doesn't go. What we have to make sure he doesn't go under these, because he's gone down into one of those pillars before, and I've had to lift the top off of this and undo all of the wiring to get him out. If you put him around your neck, he'll be content as a cucumber and warm. Okay. What was I saying? Supplementary to me. Yes. Anything you Google online, supplementary to me. That brings me to another topic, by the way. Artificial intelligence. It's out there. It's happening. I use it myself in the right circumstances. There are a few ways that I can enforce it is not used, but not in every way. So my policy on AI is this. If you need clarity on a topic, and I am not available to you, and assuming you're not working on an exam, you can use AI. If you use it to organize your notes, fine. That's fine. Use it for additional research. Use it to find a source. It's fine. The only thing in my class that I am super hard drawing the line on not using for are exams. I actually have ways hooked up to my exams of knowing if an AI was used. Pattern recognition, things like that. So don't use it there, because my policy with that is first time offense, you fail that exam. Second time offense, I request that you are removed from my class and I make a formal report to the college. So I have to come down hard on it. AI is a tool, but it is not an appropriate tool to use all the time. All right? Sound fair? Okay. All right, so this is what our schedule is generally going to look like. I don't have any dates on here. There will be dates on the version that's on your syllabus, okay? We have 8 weeks to teach this class, 16 weeks for some of my sections that are watching this online. But for those of you that are watching in my 16-week sections, where you see that there are 2 lectures in week 1, just imagine that's week 1, week 2. So take these 8 weeks and split them out to 16, okay? So today you're getting, boom, lecture 1. On Thursday you'll get, boom, lecture 2, so on and so forth, following this format for the rest of the term. Same thing is true for your labs. You will have 4 labs that are identification-based, and then a 5th lab that is about how to read maps, and then a lab exam, okay? As far as grades, who enjoys taking exams? Wow, really no one? No, me neither, okay? With that understanding, being someone who does not enjoy taking exams myself, but still being required to offer them, I only have exams as 50% of the grades in my class. Why do I have it like that? Because if you are not someone who is good at taking exams, right, you still have 50% of credit in the rest of the materials that you can do really good in to make up the difference. So as long as you're just getting by on your exams, you don't have to ace them. As long as you're getting by and working hard to ace everything else, you'll still end my class with a good grade. And the opposite is true. If you're not great at labs, but you feel like you're much better at taking exams, and as long as you're scraping by with your labs and you're really concentrating hard on acing those exams, you'll still get by in my class with a good grade. Okay, I have a split like that for a reason. You have 20% in discussions, which for those of you here in person, you do have discussion boards you'll need to work on throughout the week when we're not in class. For those of you that are watching online, your discussion credit comes from participating in the conversations in the Go React program. Okay, camera, stay with me here. There we go. And then 30%, the other 30% is in the labs. Okay, with the potential for 6% more extra credit. Okay, which can make the difference between a minus grade and a plus grade, or a C and a B, right? It can save your butt. Where does that extra credit come from? 5% of it comes from notes. I am very, very strongly in the camp that notes are an essential tool for helping you learn. I can speak at you blah, 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 all day long, and you will have forgotten most of it by the end of the class, and definitely most of it by the end of the day. Yes?
So then do you recommend that we have a journal based test? Or
What is your preferred note-taking style?
or your journal?
A journal? Do it.
Okay.
Yes. I will not nitpick your note-taking strategies. I encourage you to find a note-taking strategy. If you always have one, if you already have one, good for you. Find one otherwise. Use this class as an opportunity to find what works for you. My only rules are this, and by the way, in your Blackboard shell, you will see that in every lecture, there is a folder for you to upload your notes. I go in there to make sure that they follow my policies. My 2 policies are this. It has to be your work, not mine. That means you can't just upload a copy of my PowerPoints as your notes. Doesn't count. It has to be words that you wrote. I had one student one time who literally transcribed every word I said in class. I know, she ended up with a binder of notes that thick. I mean, she did great in the class. She understood everything. But she spent 6 hours on each lecture just writing everything down. She would go home. She was an in-person student. She would go home, watch the recordings a few times over, writing down everything that I said. It's like, okay, that's a little intense. But if that's your style, that's your style. You don't got to do that. But find your style. It has to be your work. Okay? And then my other rule is it has to be in a Word document or PDF format. If you have a MacBook, the default saving format for that excuse me, is .pages. Blackboard cannot open that. I will not be able to verify that your notes are following my first guideline, and therefore you will not get credit for it. So please, please, please make sure it's your work, and if you are on a MacBook product, an Apple product, export it as a PDF or a Word document to Blackboard. Those are my only 2 rules. Otherwise, type them up, write them down, take a picture, scan it, whatever works for you. Okay. Notes, very important. I'm a proponent of the 3-part learning method. You hear something, you write something, you share something. You hear something, you're going to forget most of it by the end of the day. You hear something and you write something, it stays a little longer in your memory. Plus, you have a resource you can look back on later. Okay? You hear something, you write something, and then you share it with someone else later, it sticks in your long-term memory a heck of a lot better. So talk about this with classmates, talk about this stuff with your friends, your family. Great dinner table conversation. You want to know what I learned about volcanoes today? Oh, that's a great starter. Okay? Do it. Okay. Also, as an added incentive for taking good notes, if they follow my guidelines, you can use them on your exams. Open note exams, as long as those notes are following my guidelines. Fair? Good. You shouldn't need to use any AI as long as you got good notes, right? Yeah, you don't want to risk that I catch with AI either. All right, any questions so far? Okay. Oh, right, I forgot to add this to the lecture, or to the PowerPoint here. As of this year, they are now requiring us to take attendance at every class section. So just letting you guys know, especially those of you that are receiving any form of state or federal funding to go to college, that funding is going to be dependent upon your attendance. So the reason why they're cracking down so hard on me taking attendance and every other professor here taking attendance is they're going to be doing much more diligent job of reporting those attendance numbers to the state and federal funders. Okay, so if you're receiving that funding, make an extra effort to be here. I'm very pleased all of you are here right now. I usually have a few that miss the first day of class. It's not a great start. This is a strong start. Good job, everyone. All right. Okay. Hello. It's frozen. Give me a second here. There we go. Okay, third time's the charm. All right, so why are you here in my class? This is a science class, which means that you are learning not just how to think about science, how to ask those questions. It's to help you learn essential skills in life. Because I'm not just going to teach you how to think like a geologist. And if any of you decide by the end of my class you want to be a geologist, sure, fine. You know, if we have a few less business administration majors at the end of the class, I'm not going to complain. You know what I'm saying? But regardless of what education or what major you are going through and what other education you choose to pursue after this, the things you learn in my class, ways of thinking, are going to be beneficial to you. Everything from medical to business to engineering. We're going to be talking about things like how to apply the scientific method, right? How to observe things, how to record those observations, how to use the properties of something that you're observing to come to a conclusion, okay? These are essential skills in life, all right? No matter what path that life takes you. So that's what you're going to be learning here, okay? You're going to be learning how to think critically and applying critical thinking skills here. By the way, one more thing I just remembered. Since so many of you are dual credit, I need to let you all know this. I don't want to use the word babysitter because I hate that, but it's been made very clear to me that as long as the dual credit students are in my classroom, I am more or less a babysitter. I fought back on that, but they said no. So I'm not allowed to leave early. I used to let all my students go early if we just finished class. I cannot do that anymore. Also, if you need to answer a phone call, you need to be in the hallway where I can see you, which means outside that window pretty much, because the frog's going to obstruct that one. I don't need to hear your conversation. I just need to see you, as long as you are not in my classroom. And if at any point you need to be taken by a parent, the parent cannot call you and say, hey, I'm here, and then you leave. Your high school, every high school has made it clear that the parent needs to tell the high school office needs to tell me. That means that they call me on that phone. And that phone is the only way that I can let any of you leave early. With the high school office tells me you are authorized. Cool. I wish I could treat you all like adults, but I don't have the authority anymore. So here we are. Okay, moving on to my standards. There's no cheating. That means that there are definitely some assignments in my class that you can work together on. Labs, huh? Sorry, was there a question?
Yeah, I have to go to the bathroom.
You do?
Yes.
You don't want to take the snake?
I don't think that'd be the best idea to take a snake.
No, you probably freak people out in the hallway. There are a few math instructors that
Don't like your snake.
don't like the snakes. Anyone else want to hold it? Yeah? Okay. Okay. Labs. Super collaborative. Work together on that. Please make study groups. Meet together outside of class time. This classroom is your resource. You can come here outside of class time whenever you want to study with the labs, to study with each other. Okay? Work on another class's homework for all I care. This is part of your home for the next 8 weeks. Feel free to think of it as such. And if I'm not here, or if it's not during a normal class time and the classroom is going to be locked, which it's usually not, I keep it open most days, let me know that you're going to be here, and I'll make sure it's open for sure. Okay? Discussion boards, you will be collaborating with each other to discuss the topic, but please make your original contribution your own work. The follow-up conversations in those discussion boards, feel free to talk with each other. Absolutely, please. That's the point. Exams, 100% only you, never anyone else. Okay? All clear on that? All right, great. Please keep your phone use to a minimum in my class, only as essential. I know that high schools have their own policies on that. The state has some policies on that. My policy is, if you absolutely have to take a phone call, outside of Lego. That's really what it comes down to. Please respect me and the time that I put into teaching. And then also no swearing in my class of any kind. This is a personal rule that I have. You are in college to elevate yourself intellectually, to think in a new way. And foul language is the way that people use to express themselves when they don't know what other words to use. And so my policy is, think of a better way to express yourself. Cool with that? Thank you. All right, and then finally, right? We're almost through all this intro stuff. My email policy is, as long as it's Monday, Tuesday, Wednesday, Thursday, Friday, I will get back to you within 24 hours. Weekends and holidays, my family is my priority. I may not get back to you until Monday. I hope you all understand that. I'm not gonna lie, in the evening, after I put all my kids to bed, I'm usually just sitting on my couch. I will usually check my email and answer stuff. That's not gonna always be the case. That's usually the case. So I'll probably still get back to you over the weekend or something. But during the week, definitely I will get back to you within 24 hours. And if I don't, please call me on it, because it probably means I got bombarded by a bunch of emails and yours fell through the cracks. Okay? All right. Yeah. Any questions about policies or schedule or how the class is going to move forward? Yes?
Do you have any policy for like AirPods or like something like that?
I'd rather if you didn't during class, but during lab time, unless you're working with a group, feel free, right? It's like, if you're just working on notes or something, you're caught up on the most recent lab, you're just working on it, yeah. When I'm not talking, and when other people aren't trying to collaborate with you on something, do what you're gonna do. Okay? All right. Any other questions? Okay. Then let's jump in. All right. How many of you have heard of geology as treated as some kind of joke before? Yes. Like in like a TV show or something?
Yeah.
Yeah. Are you thinking about the Big Bang Theory? Yeah, of course. Yeah, that's the number one that comes to everyone's mind. Sheldon Cooper absolutely bragging on geology all the time, right? If you haven't seen the Big Bang Theory, fantastic show. When he makes fun of it, I laugh, I cry. It's kind of like two different emotions there. But I mean, like in all these comic strips, treating geology as a joke, and it's because, what do? They study rocks. Right? Oh, that's not interesting. You could be studying space, you could be studying animals, you could be studying the cell, you could be studying medicine, but you choose to study rocks? Like, yeah, those people don't know what they're talking about. Okay? Geology is fundamental to so many different aspects of science. You're going to figure that out in your time in this class. And it ties into almost every other branch of science as well. All right? What does the word geology mean? So it's a combination of two words, geo, which means earth, and logos, which means discourse or discussion. Okay? So essentially that word means a conversation about the earth. You're studying the earth. You're figuring out the earth. Okay? It's conversation, which is what we're doing here. We are doing geology here right now. Okay? This is what I like to call Greek word math, where you take two different words and you slap them together and you make a new word out of it. They did that all the time. Okay? So geology is kind of a catch-all word, though, for a lot of different branches of geosciences. These are just a few of them listed here. Let's look at a few of these. Paleoclimatology. What do you think that studies? Break it down into two words. Climatology, the study of the climate, right, which is long-term trends in things like temperature and weather and things like that. Great. What does paleo mean? Huh? Don't be shy. What do you think? Remember, there are no dumb answers.
Would it be like dinosaurs or something?
It has to do with that. Fossils, but the study of that is called paleontology, right? The study of paleo. What is that, though? The word paleo means old, ancient, before, okay? Paleontology, the study of old life. Paleoclimatology, the study of old climates, okay? Okay, great. My master's thesis was a combination of the two. I studied isotope variations in fossils, which is paleontology, to reconstruct a paleoclimate model of Oregon during the last ice age. Yeah, they all tie together. Okay, let's look at another one of these. See, there's paleontology right there. What's another one here? Where is the? I know it's on here somewhere. Seismology. What is seismology? Have you ever heard the word seismic?
Earthquake.
Earthquakes! It's the study of earthquakes. Bingo. Okay, seismology is the study of earthquakes. Is that relevant here? It does. Yeah. You guys felt any earthquakes recently? We've had a couple in the last few years. Yeah, we had a 5.2, 5.3 a few years back? I was right here at this desk when it happened. My students had left like 10 minutes before. I was just puttering here, cleaning some things up, and then it felt like a truck in the building. It was like, what's that? And then I checked the earthquake sensors around the country, and it said 5 point something. It was a 5.3 in Gardendale. I was like, whoa! So, since then, I actually got funding from a national laboratory. I bought a seismometer, and over this last summer, I dug a 9-foot hole out in Gardendale, set a manhole down there, put a concrete slab at the bottom, and I installed a seismometer down there. Because of internet problems, I haven't been able to finish calibrating, get it up and running. I'm hoping to get the text today that said our IT fixed the internet. If I did, I'm going to head out there this afternoon. I'm going to get it all finished setting up, and then we'll be able to monitor earthquakes in-house instead of relying on seismometers anywhere else. Okay. So a little bit of seismology science happening out here right now. Okay, what else? Let's see. Oh, okay. Hydrogeology. What do you think that has to do with it? Say it louder. Water. Yes. Okay. Water and geology? What do they have to do with each other? A little louder. Water is found in the ground. Absolutely, 100%. We call that? There's a word for water that's in the ground. It's groundwater. No, that's actually the name. We call it groundwater. Okay, super tricky, I know. Okay, yes, water is in the ground. Not only that, but what does water do to rock? Breaks it down. We call that weathering, a concept we will talk about plenty later, okay? So yeah, water and rock, they have a lot of things that go together, and the interaction of that is called hydrogeology. So you see, all of these things are tied together. Are you playing with your fingers, or do you have a question? Okay, I wasn't sure if this was just like a hand up or not. Okay, yeah, so all of these different branches of geology, okay? And there are tons more than this. These are just a few examples. So this class that you're in right now, this is physical geology. In this class, we're going to talk about the solid components, the liquid components, pretty much every component that goes into making our Earth the way that it is. You're going to be learning about the processes that happen on the surface and underneath the surface in our current and past Earth. Historical geology kind of takes that past component a little further. We talk about all the ways that our Earth has changed over time and how they intersected with the development of life on Earth. Okay? Because those two things are fundamentally connected and have been for billions of years. It's fascinating. I really hope you take 1404 from me later. Okay. All right, so first thing, Earth is dynamic. Dynamic is a word that means characterized by constant change or activity. Who can give me examples of the ways that Earth is dynamic? Are there any things that change here on Earth? Shaking your head, Mia. What do you got?
Like, you know, like when we have earthquakes and stuff.
Sorry, can you say that a little louder?
Like when we have earthquakes, like obviously to change.
Bingo! Earthquakes! A change, a shift in the Earth. That is absolutely a change. Great example. What else?
Climate.
Climate. Absolutely. I didn't say only having to do with rocks, right? No. Earth is dynamic. Climate is a component of the Earth process. Bingo. What else? Volcanic eruptions. These are great. Any other examples? Yes? Biology. Biology changing is a component. You and I are dynamic too, right? If I turn the temperature in here down 20 degrees, what would she do? Angelina. If I turned the temperature down here 20 degrees, or if I turned it up 20 degrees, I should say, what would you do? You'd be really hot, right? Would you take off your sweater? That's what I'm going for. If I turned it down, let's see, does anyone have a sweater just sitting around anywhere? You guys, okay. If I turn it down 20 degrees, would you put it on? Are you changing? Yes, you and I are very dynamic. Life is dynamic. We adapt, right? Okay. So, some examples, things like earthquakes, landslides, tectonic movements. You're going to get sick of me saying the word tectonic in this class, by the way. It has to do with a lot of stuff. Transgression and regression. Anyone want to guess what that is? Transgression is the rise in sea level. Regression is the drop in sea level. Happens all the time. It's happening right now. Yes? Yes, you may. Yes, it's happening right now. We're experiencing a transgression of sea levels right now. Ocean levels are rising. Just go to Venice. You'll see. Right? Okay. Volcanism. Someone said volcanoes, right? There are also, those are big scale things. There are also tiny little small scale things that happen as well. Things like lithification. Lithification is the process by which you go from having loose sediment like this sand in this jar, which is from Pensacola Beach, okay? Look at that beautiful white sand, right? Just makes you want to go to the beach right now, doesn't it? Think about next summer. Okay, all that loose sand becomes sandstone. How do you go from this to that? It's a process called lithification. Okay? It takes a very long time. Pressure, heat, squeezing water and air out between all the particles. A little bit of cement gets in there, some naturally occurring cement that binds it all together, and boom, bada boom, you get a rock called sandstone. Okay? Long-term, small-scale processes also are included in how dynamic Earth is. Erosion, the transport of the sediment, the transport of a single grain of sand across the United States through the Mississippi River, right? That's erosion. That is an aspect of how dynamic Earth is. Earth is constantly changing, okay? All right, so you can kind of think of these changes in two different contexts. You've got your larger kind of global scale events. Your things like earthquakes and volcanoes, things that are felt or the influence of those things is seen in some way around the world or a large part of the world, right? That includes things like general climate change and such. Then you've got your micro scale events, the things like weathering, erosion, fossilization. Do you guys know how fossils are made? How? There is pressure, yes, that's true, and it does require the presence of that sediment. It's not quite the same as lithification, though. In fossilization, every cell is replaced with mineral. In the highest quality fossils, it's literally, you can look at it down to the cellular level, and you see little minerals in the shape of the cells that were replaced. Okay? That is a process that takes time on the micro scale. Okay? So, something I hope that you've picked up on here is that geology is a combination of the other fundamental sciences, the physics, the chemistry, and yes, biology. I like to say geology is the marriage of physics and chemistry, where biology is that favorite brother-in-law that comes to sleep on the couch all the time. Okay? You can have geology without biology. I mean, look at the other planets in our solar system, right? A bunch of them are geological. Actually, almost certainly all of them are to some extent. And I told you I bring up planets and space and stuff at some point, right? What are the rocky planets in our solar system? Mercury, Earth, Mars. Did we miss one?
Venus.
Venus, there it is. Yes. Okay, those are the 4 rocky planets. What are the other ones? Jupiter, Saturn, Neptune, Uranus. Okay? Sorry, Pluto, not currently in the club, right? For reasons I can talk about later when I have time for another tangent. Okay? But even those gas giants, for all those gases to have formed in those spheres, they had to have been pulled there by some form of gravity. That gravity has to come from mass, which means that almost certainly every single one of those gas giants has a solid core. Okay? So there is probably also a geological component to those as well. So every planet in our solar system is geological, but that does not require biology. The only planet that we can confirm has biological components to the geological system is Earth for now. We'll see how Mars turns out. Okay. Let's talk about the people who got the ball rolling on studying geology. But before the study of geology came the study of science. And before the study of science, you had these guys called natural philosophers. They were not actually scientists. For scientists to be a scientist, you have to have a process. The guys that came first didn't really have a formalized process of study. They just kind of made observations and then came up with answers based on what the best general understanding at the time was. An example of this, Aristotle. Okay? Aristotle, who was alive a very long time ago, that's BC, by the way, so we're talking almost 2,500 years ago, right? Natural philosophers like Aristotle, people would come to them and ask questions about the natural world. And they would give an answer based on what the best general understanding of the world was at the time. For example, it is recorded that one person came up to him and said, "Hey, what's a volcano?" Well, if you are a Greek living in Greece in the 300s BC and you look at a volcano, which is this giant mountain that spews fire out of a hole at the top, what's your natural conclusion going to be? He told them that it was a doorway to hell, basically Hades, right? Clearly, a hole in the ground that fire comes out from, that has to go to Hades. It made sense with the understanding that the society had at the time. But it was a question that was asked and an answer that was given. However right or wrong it was, it started setting the foundations. Another time, someone brought me fossil fish. This is a story. I don't know if this is verified. This is a story that goes around the scientific community. Someone brought Aristotle a fossilized fish. Okay, so it's the skeleton of a fish in the rock. And they said, "The heck is that?" Probably not with those words, but you know what I'm saying, right? I translate it. And he said, "Well, it's clearly a fish skeleton, but it's in rock, not in the ocean. The only logical conclusion we can draw is that there are fish that live in rock, and you found it dead." It makes sense with what they had at the time. Okay? They didn't understand how old the Earth was. They didn't know what fossilization was, what liquefaction was. All they knew was that clearly a fish, it's in a rock, must have lived there. Okay? But that laid the foundation for what would come later. People actually trying to quantify their answers. There's this guy named James Ussher, and I know very well when I just said the name Ussher, a bunch of you thought this guy. Not him, okay? This guy, okay? He was a priest, an Anglican priest who lived in the 1600s. Now, he approached this from a different perspective. He approached the idea of how old the Earth is, but he tried to use documentation to prove how old the Earth is. What document would an Anglican priest attempt to prove the age of the Earth with? The Bible. And you can, actually. We know how he did it still to this day. If you go back, have any of you ever read the Old Testament? If you read it, it's like there are entire books that is like, this person begat, this person begat, this person begat, this person begat, this person. This king reigned for this many years before his son took over, who reigned for this many years, right? Just go through Leviticus and Acts and not Acts, but you know, all of the Old Testament stuff, and it's like line after line after line, chapter after chapter of genealogy, which is fascinating. But what he did was he took all of that and he more or less estimated ages of people, generations of time, back all the way to the first person who's recorded in the Bible, Adam. And what he came up with is that the date of creation was 4004 BC, October 22nd. I'm not entirely sure how he came up with October 22nd. I think he actually also said like 9:30 a.m. I have no idea where he got that. I don't even know how he got October 22nd, but the date of 4004 BC he got from those generalized dates he got from the Bible, which is where the common Christian belief that the earth is 6,000 years old comes from. A lot of Christian denominations still hold to that. The earth is 6,000 years old. Came from this guy. Why would so many Christian denominations around the world believe this? What else was going on in the 1600s? What in particular was something that was going on in and from Europe that was often funded by the Catholic Church? The largest Christian organization in the world at that time. What was England, Spain, France, Portugal? What were the Dutch doing? What were they all doing in the 1600s? Huh? You can say it. Like, it's not like...
I don't know if it's the right
Do it.
I don't want to be wrong.
I promise no answer is going to be wrong. Just might not be the one I'm looking for.
Was it when they were instead of we were doing science, getting into science and the arts instead of like
That was in its infancy. That's not what I'm looking for. That was in its infancy. You had a few other people who were diving around what science really was. Not there yet, though. What were they doing with ships? I thought I heard you gasp. And I was like, oh, she gets it. Colonizing. Every single European country that had a navy was going out exploring the world and saying, this is mine, that's mine, this is mine, this is mine. Oh, you people are here already? Well, you're mine too. And what they take with them? Christianity. And what did they come with it? The earth is 4004 BC, that's the date of creation, and that's why so many people around the world still hold to the earth is 6,000 years old philosophy. Okay? Believe me, we will spend time on that. And I do actually need to put a little caveat here. At no point in my class is anything that I teach supposed to persuade you or dissuade you from any previously held belief. Okay? That's not my goal. My goal is to teach you science as we currently understand it. Where science and general religion seem to disagree, I am not going to spend time on trying to convince you one way or the other. I'm just going to tell you the facts as we have it in the scientific community. All right? If you want to have a conversation about how that might relate to religion, I'm happy to have that conversation outside of normal class. I personally have my own religious beliefs. I am religious. If you would be interested in knowing how I resolved that to science, I am always happy to talk about it outside of class. Okay? All right, so after Ussher and all of this colonizing took all of this belief around the world of the earth is only 6,000 years old. Well, it was a little less back then, right? Like 5,500 back then. But after all of this went around everywhere, eventually things started to break down. People started to ask questions. The question of, well, if the earth is this young, where's this volcano come from? How did this canyon form? Right? The answer to that was catastrophism. Okay? Catastrophism is the belief that these massive, large geologic structures, like a mountain range or a volcano, happen through gigantic catastrophic events. A mountain range is raised in a few days because of this massive earthquake. A gigantic, once in a 1,000-year flood carved this valley very quickly. Okay? That's how all of these gigantic things form. Well, catastrophism satiated everyone and their questions for a while, until 100 years or so had passed, and no one had witnessed any of these gigantic catastrophic events. Then you have people asking questions again. People like James Hutton in the 1700s. Okay? Hutton was a Scottish geologist. You'd be actually surprised how many of the classic geologists, fathers of geology, came from Scotland. Until you go to Scotland and you realize how much incredible geology there is there. It's fascinating. I have so many pictures. Okay? But he actually tried to quantify his data. He would ask a question, and then instead of just coming up with an answer, he would go and observe stuff to come up with an answer. For example, how much sediment moves down this river? And he would observe it. And he would record that data. And he spent decades recording data before he published his results. And his results, guys, blew Usher's date out of the water. I want to say, I don't remember the exact words, I think it was in the ballpark of, he said, based on my observations, the Earth has to be at least 200 million years old. Which, going from 6,000 to 200 million, you know what everyone did? They laughed in his face. Even the rest of the scientific community at that time said, okay, we don't think it's 6,000, but you're going a little overboard, don't you think? Okay? But he had data. And eventually, they had to acknowledge, okay, there's something here. His data is hard to argue with. And that's when it really started to catch on. You collect data. You make an observation. This is the beginning of the scientific method. Okay? He is one of the fathers of the scientific method. The first principles formed before him, but he was one of the first people to apply it in its entirety, at least within a geologic setting. Okay? He came up with a few very important key pieces of geological principles. Okay? One of which was he helped contribute to the principle of uniformitarianism. Now, I need to say this. There are very, very few things in my class that I need you to know word for word. I never need you to memorize anything. This is where taking good notes comes in. Okay? The principle of uniformitarianism is something that you need to know word for word. So if you have somewhere to write it down right now, I encourage you to do so. You change one word in this and the meaning changes. It is very concise. The principle of uniformitarianism. Physical, chemical, and biological laws that operate today have also operated in the geologic past. I don't know if I have any paper. I've got pens, but I don't know if I have any papers. Give you all a second to write that down. Physical, chemical, biological laws that operate today also operated in the geologic past. We good? Okay. So what does that mean? Let's break it down. Every time I say break it down, I half expect someone to start dropping a beat, but no one ever does. Disappointed again. Chloe looks like she can drop a beat. All right. What does this mean? Say that again, sorry. What about information?
I just know it has to do with information.
Definitely does.
Specifically like chemical and biological laws that are applied down to the house and so
Yeah. If I observe something today, does it not logically follow that it also happened back then? So, if I'm James Hutton and I'm looking at how much sediment washed downstream over the course of a year, what can I do with that information? I write it down. If I say 10,000 tons of sediment washed down the Mississippi River, he's in Scotland, so the Mississippi isn't what he looked at, but you know what I'm saying, right? Washed down the Mississippi River over the course of 1 year. What can I do with that information? If I assume that the same rate of sediment removal has been happening, what can I do with that?
But what you believe in, he said that it was older and showing more using it.
This is where he got that date from. You do something like this. I say 10,000 tons washed down the Mississippi River every year, and then I go down to the bottom of the Mississippi where all that sediment is getting dumped, and I estimate that there's 40 billion tons of sediment at the bottom of the Mississippi. All I have to do is divide 40 billion by 10,000, and that tells me approximately how many years I think the Mississippi has been dumping sediment there, huh? This is where you get something like the Earth is X amount of years old. This is where that data came from. What is something else that we can maybe draw from this? What's the next step? Physical, chemical, and biological laws that operate today also operated in the geologic past. That's the next logical conclusion. What can we think about? These forefathers didn't so much. We could apply that principle to something else. I mean, all of it, yes. I'm not thinking so much about a physical thing, as much as a temporal thing. Physical, chemical, and biological laws that operate today also operated in the geologic past and will continue to operate in the geologic future. And this is where something like geologic forecasting comes in. How can I be sure that there will be an earthquake in this location within the X number of years? Because it's happened already, and I have all the data to prove that it has. In this sequence, I take this concept, and all I do is apply it forward instead of just looking to the past. Geology isn't just about the past, my friends. We learn about the now and we learn about the future. The science is the science is the science. Okay? Fundamental concept here. Okay. So, that was Hutton. Through his studies, we know something like the Grand Canyon doesn't have to form through a gigantic flood that happens once every 1,000 years. It can start off looking like this. And then over 20 million years, you get a Grand Canyon. Okay? You see the importance of all this? How this evolved science, not just geology. Understandings of biology, too, came with this. A broadening of the scope of everyone's perception of physics and chemistry in general. When you understand that the Earth isn't just 6,000 years old, so many more things made sense in science. And that's where science kind of exploded, okay? That was an industrial revolution of science that happened right there, okay? All right, so now let's talk about geologic time. How old is the Earth? Well, according to our modern science, the Earth is about 4.6 billion years old. I'll give you the exact date in a little bit, but I'm rounding it to 4.6 billion for now, okay? We know this for a couple of reasons. I'll teach you about the different ways that we measure time. Okay, a few right now, just the easiest ones to comprehend. The law of superposition. The law of superposition simply states that whatever is on the bottom is oldest. Simple example. Here I have two cloths. I'm holding them equally. Which one was there first? The one on the bottom. How do you know that? I mean, yes, you saw it. If your eyes were closed and it did the same thing and you opened them again and it was like this, how would you know the one on the bottom was there first? Right. Without someone doing that, it has to have been there first. And in nature, there's no one doing that to layers of rock. Okay? Which means that whatever is on the bottom, 99.99% of time, is going to be the oldest. That 0.001%, not something you really need to worry about in this class. I will just say the only exception to that rule is when there are tectonic forces, there's that word again, that take this and flip them over. That's where things get confusing. I'm not doing that to you guys in this class, so don't worry about it, okay? No, that's deeper concepts of geology. I'm just letting you know. That does happen 99.99% of the time. Law of superposition holds, okay? All right, so this Permian layer is older than this Triassic layer. So A is older than B, is older than C, is older than D, is older than E, so on and so forth. Have I beat that dead horse enough? All right, good. All right, now let's talk about the principle of fossil succession. The law of superposition is great for helping us resolve the general ages of things sequentially, vertically. Not so much across distances. Okay? We need something to help with that. So fossils comes in here. Okay? With fossils, okay, I was like, where's this thing? Okay, with fossils, I can look at how widely distributed one particular type of fossils are, one species of fossil is. Okay? And then where I can see it end and another species of fossil begin there, I know, okay, I've shifted habitats. Not time, though. Time across a horizontal layer is consistent. Where my fossils change, I would interpret that as something like a climate change or a habitat change. Okay? So knowing this, I can look at my layers of rock and I can see where the different fossils are. And where those different fossils change, I can interpret that as a distance shift. So if I am, let's say I'm right here, boom, I poke a hole, drill down a layer of rock, 100 feet down, I find fossil 1, okay, in limestone. Okay, now I go 100 miles this way, drill down 100 feet, find the same layer, but now it's sandstone. It's at the same depth. And fossil 1 is still there. Doesn't matter that this one's limestone and this one is sandstone, fossil 1 is still present. What does that tell me? Same age across distance. So we'll use something like the law of superposition to interpret vertical age relativity, and then we'll use something like the principle of fossil succession to interpret horizontal over distances age relativity. Okay? So those are just a couple of different ways that we can do that without needing to include anything like numbers. Okay? I don't need to say it's X amount of years old. I just need to know if they are the same age or they're not the same age using those two types. Any questions so far? Okay. All right, so I'm going to take a pause here and we're going to explore for a minute exactly how science works. Yes?
So since we're in the Permian Basin, right, the rocks here found in the Permian era.
Good question. You noticed I said that word Permian earlier. Yes. There is an entire period of time in geologic history called Permian. The Permian Basin is named after that, not the other way around. We live in the Permian Basin, which is called such because almost all of the rock that is in this basin that contains oil came from the Permian time period. And that's something we explore way deeper in 1404. Okay? All right. Any other questions? Fantastic question. Super glad you noticed that. You're paying attention. Any other questions? Okay, so let's talk about how science works. What's the first step of the scientific method? Gather facts, yes. Let's have an exercise in this. I'm going to give each of you a mysterious object. I have 12, and there's 13 of you, so someone's going to have to share eventually. Would you mind sharing this? This mysterious object we know nothing about. We are simply going to describe it. Its facts, its characteristics, its properties. You have never seen this thing before in your life. Does it have a function? We don't know. Let's use science to figure it out. Tell me some facts about this object. Okay. Borrow your mysterious object real quick and really quick show it to the camera. Hey, over here. Thank you. Here's the mysterious object. It's probably focusing on me. Or I don't know if I can stop it. Okay, this is the object we are going to identify. You can feel free to pause the image there. Try and hold it still. Pause it there. Participate in this conversation. All right. Okay, thank you. All right. Give me some facts about this mysterious object. It is round. Is it round? Spherical. Round is a two-dimensional expression. Spherical is a three-dimensional one, right? Gotta be specific. Okay, it is spherical. What else? It has little dents, like little divots in it, okay? It has little divots. Are those divots covering the entire surface?
Yes.
All over. Okay. What else?
Some divots are smaller and some divots are bigger.
Oh, they're not of equal size. Let's put that as a subcategory. Not equal size. Okay. What else? Huh?
Bounces.
It bounces. What might that mean? Huh? Okay, we can start trying to make an interpretation about the materials involved. There are some things that we can absolutely eliminate. It's clearly not made of metal. It's made out of materials that when a little bit of force is applied, it will rebound. Plastics, rubbers, things like that. Okay, it's bouncy, so soft materials. Materials, and we can, this is just conjecture until we do some sort of material analysis. We can say probably plastics or rubber, right? What else? It's white, sure. We can notice the color, absolutely. You can squish it? Girl, you've been doing those like hand crunches?
No. I'm saying you can't squish it.
Oh, you can't squish it. Okay. All right. I was gonna. It's just like I'm going to watch her actually crush that thing. All right. Okay. So you can't really squish it, but it does bounce. Okay. So that gives us kind of an interval of force required to make it do that rebound effect. You can't squish it with your hand. That tells us a Newton cutoff, right? We can measure how many newtons your hand can generate in force. That's not enough. But the amount of newtons it experiences when it bounces off a flat surface clearly is enough to make it deform a little bit to rebound upward. Okay, so we can measure that and find an interval within which that deformation occurs. Okay, so now we're starting to actually have measurable data. Great. Is there a hypothesis yet for what this might be? We have some facts. Would anyone like to give us a hypothesis based on these things? Huh? What is a ball? I mean, technically, a ball is simply another description of a sphere. It is a sphere with a function. And that function is? Sports. Does it have to be, though?
No.
It's one. Okay, so our hypotheses. Sports ball. What's another one?
You can collect them, and some people collect things that are sounding, stuff like that, so they can be collectible.
It's a little more conjecture without any data behind it. What's another conclusion we might draw from this? Are there functions that other balls fill? I would put probably toys in the same realm as sports balls, yeah. Musket balls. Wrecking balls. There are plenty of balls. Could it be a weapon?
Yes.
Yeah, it could definitely be a weapon. Could be. What else? Any other ideas before we move on? Okay, let's just push forward with these two. How would we go about testing these hypotheses? Because that's our next step. We gathered facts. We made a hypothesis using the data, but without testing the data. The next step is testing your hypothesis using observations not used when we gathered the data. How can we test these two hypotheses? Yes?
You could throw this at the water bottle.
Would throwing it at the water bottle give me a substantially quantifiable reason for whether or not it is a weapon or a sports instrument?
A weapon.
I mean,
Because you can't.
it would. There are plenty of sports balls that could destroy the water bottle as well as the weapon could, right? What? But I like your idea of throwing it at something. We propel it. We use some form of propellant. Okay? Maybe we have compressed gas. Maybe we use gunpowder. We have all sorts of different things to determine, does this best perform as a sports instrument or a weapon? See how this works? We're gathering more data. Now, if I use compressed air to boom, shoot it at something, let's say I shot it at a brick wall, what would happen? Unless I used enough force, then what would happen? No.
Oh,
No, if we shot this thing at a brick wall with enough force, we would find that thing quickly breaks. It does not have enough force. So if I shot it at a brick wall, that's what VW is doing here, okay? Up to a certain point, it's going to break. If it can't even go through something like brick. And if we shoot it at a person, let's ignore the Geneva Convention here, okay? We're shooting it at a person as a test. It might break bones, but it's certainly not going to do something like penetrate the skin until you reach a certain point, right? An excessive amount of force would be required to do that. But as far as our brick wall experiment goes, it's going to break on the wall. So if it breaks on the wall, and it takes a lot of force to make it actually hurt someone, is this an effective weapon? But if you hit it with enough force, just enough force, you're going to find it goes real far. And let's say that we took another equivalently sized ball, made out of the same approximate material, but we left off the divots. What would we find? We dropped our ball. My floor is clearly not level. It's rolling over there. What would we find? The one without divots does not go as far as the one with divots. Our mysterious object. Okay, it flies. Okay, it breaks on that. It's going to fly far. So, knowing that it breaks upon contact with anything harder than its own material, and knowing that it flies much further than an equivalently sized ball without any divots, what can we then assume of our two hypotheses here? It's a sports weapon. It's a sports instrument, not a weapon. We don't know for what sport yet, but that's besides the point, right? We have identified what type of object it is. All right, the big reveal. It's a golf ball. You guys had no idea. Okay, good job. Thank you for figuring it out. All right, I'll collect this then. Okay. Thank you. Any questions about the scientific method? This is going to be something that you actually apply in the labs. You're going to be getting samples that you need to observe the properties for, which I will teach you about. I'm not just throwing them in blind. Okay? You're going to observe the properties for those samples. You're going to record those samples, properties. Then you're going to make a hypothesis about what it is based on the resources that I give you. And what's the test of your hypothesis? You turn it in for a grade, and I tell you if you're right or wrong. Scientific method. Okay? All right. Another simple example of this. Let's see. Greg, you're wearing glasses. There's two reasons why Greg might wear glasses. He could be really hipster, or he might have poor vision. How would we test those hypotheses? Take off the glasses, make him walk across the room, see what happens, right? If we did that, what would happen?
I would make it to that.
You would make it to the end of the room? Would it be easier with or without glasses?
Roughly the same.
Roughly the same? I chose the wrong person. All right, yes.
You can make them do a test, like look at.
Yeah, how do you read something across the room? The optometry test, exactly. We can do all this stuff, right? And eventually we would find, do you wear them because you're hipster or because you have poor vision?
Poor vision.
Poor vision, there you go. Boom. Okay, simple example of that. I'm not going to make him do that. I'm not cruel. How did the hipster burn his mouth? He ate pizza before it was cool. I know. All right, y'all better get used to it. I pull dad jokes out every now and then. Sometimes just to make sure you're awake, sometimes just because I want to. Okay. So, now we understand the scientific method. Let's get back to talking about Earth. Earth is separated into what we typically refer as spheres, okay? These are not the layers of Earth. We will talk about the layers of Earth here in a few minutes. But the spheres of Earth are the different, I don't want to use the words realms. That sounds too fantastical. But the different sections of the way that Earth's systems interact with each other, okay? So for example, we have, first of all, I still have all this up here. Hold on. Before I go into each one of these, this is a picture called the Blue Marble. It was taken in the early 70s, okay, during one of our space missions to the moon. I could probably get a better one now, a more recent mission. I haven't replaced it yet. This is a beautiful picture, though. Describe what you see.
I see clouds, I see water, I see grass, I see land.
You see grass?
Yeah, I see grass.
Oh, yeah, look at all that. Probably not grass. It's probably, rainforest. But, yes. And Serengeti. I mean, there's probably some grass there. There's a lot of that trees, though. But yeah, you're absolutely right. You just named all four spheres. Okay? The hydrosphere, which is all that water. The atmosphere, this is the clouds. The geosphere, which is the land. And the biosphere, which is the life, the green. Okay? So, your hydrosphere, it encompasses all water on Earth, wherever it is. 71% of our planet's surface is covered in water. Did you know that? Weirdly enough, that is also how much of our bodies is water. About 70 to 71% of the human body is also water. Interesting. Coincidence? Yeah, probably. All right. And then there's the atmosphere, which is actually about 100 kilometers thick. If you've ever flown on an airplane, how many of you have been in an airplane? Okay, great. A lot of you. Okay. If you've ever been on an airplane, most of the time, when you're flying in an airplane, you hardly ever leave this thin orange layer above the surface. Okay? But the atmosphere keeps going way, 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 way up, 100 kilometers up. Okay? I mean, it gets thinner, and eventually you'll reach open atmosphere or open space, but it does go up there. Then you have your geosphere, which is separated into these distinct layers: the crust, the upper mantle, the outer core, and the inner core. Believe me, we will learn all about that stuff. Okay? And then we have the biosphere, which is all life on Earth. When you think about it, life on Earth is kind of a combination of all the rest. Think about us, right? We're 70% water, 71% water. That's hydrosphere. Atmosphere, I'm breathing it, putting it in my bloodstream. Okay. Geosphere, you eat food. That food has minerals in it. Your water has minerals in it. Okay. That's geosphere going into you. You're kind of a conglomeration of all the spheres when you think of it like that. Now, all these spheres are constantly interacting with each other, like they do in biology, right? Water is going in the atmosphere, then raining down into the geosphere, so on and so forth. The interaction of these spheres makes what we call cycles, okay? So you've got different cycles like the hydrologic cycle, which is the water cycle that you probably learned about in grade school, okay? Water goes into the clouds, it rains down, its runoff goes to the ocean, evaporates, precipitation, runoff, evaporation, precipitation, runoff, all of that. That's a hydrologic cycle. The geologic cycle, which we will spend some time on in a bit, includes the aspects of the hydrologic cycle: weathering, erosion, metamorphism, melting rock, the formation of magma, that cooling magma back into new rock, things like that. It's the geologic cycle, the rock cycle, okay? Now, all of these cycles require energy. Energy comes from two different places for all of this. If my slide will catch up. This is the beautiful part of education. Our technology doesn't get replaced very often. This is a 6-year-old laptop and it's feeling it. Okay. Okay, so the first source of energy comes from the sun. Okay? The sun is what gives the energy for all of the exterior cycles that we see. Changes in weather, tides, currents, all of that stuff is given energy by the sun. Weathering and erosion that happens up here on the surface. Energy from the sun. Okay? The energy for things like earthquakes and volcanoes, tectonics, that comes from interior energy, coming from inside the planet. Now, that energy is primarily radiation energy, actually. Why would radiation be coming from inside our planet? Any ideas? First of all, let me clear the air here. Do we know what radiation is? What is radiation? Who feels comfortable giving me an explanation of that? Or feels uncomfortable doing it, but we'll do it anyway? It's not a toxic gas. There can be radioactive gases, but radiation itself is not a gas. Yes? UV rays? Yes. Ultraviolet. Any light is radiation. Technically. Radiation is an energized particle that is traveling with some force, some kind of velocity, okay? Everything from radio to ultraviolet to alpha, beta particle, which is the damaging stuff, the stuff that'll kill you, okay? That's all radiation. Now, the radiation I'm talking about comes from isotopes, which we will go into more depth on later. But those isotopes are deep underground because they tend to be heavier than the rest of the elements. And so they sunk towards the middle of our planet as it was forming. Because all of that radioactive stuff is down there, that radiation keeps everything hot. And that heat emanates outward towards the surface, and that's where we get volcanic energy and seismic energy, tectonic energy, and all that stuff. Okay? That radiation being the cause. All right. The rock cycle. Rocks and minerals are two totally different things. I want to get that clear right now. We'll talk more about that later. But a rock is a collection of minerals, and a mineral is a single unit of a substance that has a definition. Okay? There are three types of rocks: igneous, sedimentary, metamorphic. I'm going to give you a brief overview of the rock cycle right now, and then we will spend the next 3 weeks going over each component individually. Okay, so you have a firm grasp of what they all mean and how they work together. Okay, I like to start with magma. This melted stuff, melted rock that Energy from deeper underground has melted some body of rock. It has risen up to the surface because it is less dense now that it's in a melted state. Just think of a lava lamp, right? Okay. But now it's up here near the surface, and some of it pops a cork and comes up to the surface, where it crystallizes. Some at the surface, some below the surface. Eventually, it's going to lose that energy, and when it does, it recrystallizes back into rock. We call that cooling or crystallization, and the resultant is igneous rock. That's your first type of rock. Igneous rock only comes from the cooling of magma or lava. You guys know what the difference between magma and lava is? Louder, I'm sorry.
One's a liquid form and one's a solid form.
They're both in a liquid form. If it becomes a solid form, it's an igneous rock. They are the same thing. Magma is what we call liquid rock under the surface. Lava is what we call it when it reaches the surface. It's the only difference. Okay? Okay, so igneous rock, boom. It goes through weathering, erosion, and deposition and becomes sediment. It gets broken down by all the things, how dynamic Earth is at the surface, breaking it down into sediment, right? Like sand grains we talked about before, okay? So you get piles and piles of it, layers and layers and layers of it, making sedimentary layers, which then go through lithification, become that sedimentary rock, right? That sedimentary rock, then, as it gets buried deeper and deeper and deeper, gets heated and pressurized and changes its form physically and chemically through a process called metamorphism. And it becomes metamorphic rock. If you continue to heat it and bury it deeper and deeper, eventually it's going to heat up to the point where, guess what? You reach the melting point and you're back up here to magma. This is your generalized rock cycle, but it doesn't have to go through all of those steps. There are steps we can skip. There are steps we can't skip, but there are definitely steps we can skip. The ones that make sense. For example, sediment can become sedimentary rock, and then if that sedimentary rock is pushed to the surface instead of deeper, it weathers back down into sediment. It can just keep doing this. Your metamorphic rock, instead of getting pushed deeper to the point where it melts, can get pushed to the surface and turn into sediment again. Your igneous rock, instead of weathering and breaking down into sediment, can get buried deeper and become magma again. There are steps we can't skip, though, without breaking certain rules. Igneous rock will never form from sedimentary rock or metamorphic rock, only from magma. Okay? Sediment can come from any three types of rock, but sediment will never become magma without first having gone through the metamorphism process, because you have to heat it up to get there. Okay? Even if for just a brief moment, it will change physically and chemically and then melt. Okay? So there are some parts that make sense to skip and others that you physically cannot skip. Okay? Without breaking our cycle here. You good on this? Any questions about the rock cycle? Good. I forgot to keep tabbing through all that. Alright. Yes. Ruh-roh, it's stuck again. Bop. Alright, so let's talk about the history of Earth by starting with the history of the universe. Okay? So, the current dominant theory on the universe, how it began and how old it is called the Big Bang Theory. Okay? The Big Bang Theory states that the Earth is the universe is approximately 13.7 billion years old. Depending on which physicist you ask. The oldest light that we can observe is 13.7 billion years old. but for physics reasons, it's probably older than that. That's just the oldest life we've observed. Okay. So what happened here was you get this gigantic explosion of hydrogen. Just the most basic element ever. Proton. It's pretty much just a proton flying out through space. Okay? From this tiny little dot, who knows how big, came all of this hydrogen exploding outward from the central point. And as it spread out into the universe, what was incredibly hot, I'm talking about like billions of degrees Celsius, okay? Starting here, spreading out, the further all of that stuff spread apart, the cooler it all became. Which means that as it became cooler, it became less energized. As it became less energized, other forces started to take over. When you super energize something, it doesn't want anything to do with anything else. Those hydrogens were zipping as far away from each other as possible. But when you cool it off and it enters a lower energy state, other forces take over. Forces like gravity and electromagnetism. So what happens is each one of these hydrogen particles has an electromagnetic charge. And as all these hydrogens spreading through the universe cooled off and allowed the electromagnetic force to take over, they started to coalesce towards each other, drawn towards each other electromagnetically. And the more of those hydrogen atoms came together electromagnetically, the more gravity they produced. Gravity is a force that depends on the presence of mass. I have gravity, you have gravity. The only reason why we're not being pulled towards each other is because there's a larger source of gravity nearby, which is the Earth, right? If we were in deep space, we'd probably be orbiting each other, okay? Pulled towards each other, okay? As more hydrogen particles came together and made a larger source of gravity, it pulled more in, more hydrogen, more hydrogen, more hydrogen, more hydrogen, to the point where this cloud of hydrogen became so dense that it entered a supercritical state, so compacted together that it started generating that initial burst of heat again. Okay? It started having enough energy to rip apart and reform. And so you produce fusion. Fusion is the nuclear force that combines atoms together. So, two hydrogens combine together into what? For this, I need my stick. Stick acquired. All right, camera, follow me. Thank you. Two hydrogens, two protons essentially, combine into what? What atom has two protons? Helium! Bingo! The first heliums start to form in these first stars. Hydrogen atoms come together, form your first star. The star, through fusion, takes those heliums, or those hydrogens, makes helium, and a heck of a lot of energy as a result. Okay? So, this first generation of stars starts burning hydrogen to make helium. Eventually, you run out of hydrogen. Your star stops burning. A couple of things can happen. Your star either explodes through what we call a supernova, which is basically when it's got so many heavier particles in it, generating so much gravity, that the gravity reaches a critical point where it collapses everything in on itself and makes a gravity wave outward as a result, which blasts the outer layers of the star apart, making a supernova, which takes all of your heliums and remaining hydrogens and spreads them through the universe again. Then the same thing happens. Electromagnetic forces pull them together, you make a new star. This time, it also includes helium. What happens when you fuse heliums with hydrogens? What's one proton plus two protons? 3 protons. And you get lithium. This is how it goes. This is called the R process. Every single element in our universe started through this. Okay? The last element that you can actually make physically through the R process is iron. processes later on that happen created the rest, okay? But eventually, you have all of these different elements blasting through the universe as a result of stars being born and dying and born and dying and born and dying. So here you are, 5 billion years ago, when our star is born. Our star is made out of all the same stuff that's made in the rest of the stars before it. Every element on here going up to iron. In our star. What color is our star, by the way? What do we think?
Red.
Our star is red? Who agrees or who disagrees? You agree? If our star was red, we would not see white. Everything would be red. Because that would be the wavelength coming off our star. Yeah?
Like it has color, but it's what we can see with our eyes. And then some stuff sleeping.
Which is what? What is the color of our star? White. Thank you. No one said yellow. It looks yellow through our atmosphere because our atmosphere is diffusing the light for our eyes. Our star is a white star. Okay? If it wasn't, then there would be nothing white around us. Paper wouldn't be white. Snow wouldn't be white. Okay? The reflected light from the sun would make it that color. Our star is white. Therefore, we have the color white on objects with no color, or with every color, I guess technically. Black is the absence of color, not white. But you know what I'm saying, okay? It is a white star. But there are red stars, there are brown stars, there are blue stars. Interestingly enough, no green stars. The wavelength of the color that your star produces is based on whatever phase of its life it's in, because that's determined by what the dominant outermost layers of gases in it are. So like a red giant has a lot of iron in it. It's at the end of its life, right? Ours has a lot of calcium in it right now, and so it's white. Okay, it's got a lot of other things going on in there, but it has a lot of calcium in its outer layers, so it's giving off a white wavelength. Okay, but there aren't really any elements that I'm aware of anyway that you can produce in a star that make a green wavelength. Haven't heard of any anyway. Okay. Anyways, okay, so now our star has formed 5 billion years ago. Around the star that is producing all this gravity is all the leftover stuff that didn't get pulled into it. A bunch of debris, cosmic debris, comets and asteroids, maybe even other planets from older star systems get pulled towards this newly formed star. And they all start circling this star. We call this the nebular theory, where you go from just a cloud of gases to a star with a cloud of stuff all around it, a disk of stuff all around it. And eventually, all the debris in that disk resolves into planets. Boom, 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 boom. Early on in our solar system's history, we believe we had several dozen planets. What happened to them? Huh? They collided? Absolutely. A lot of them that probably happened.
They floated away.
Some could have floated away. They were a little too far, and they just kind of drifted off, perhaps. Some probably got pulled into the sun. A little too close. Some probably got pulled into Jupiter. Got a little too close. Jupiter is the second largest gravitational force in our solar system, right? So, we get all these planets that form, and eventually, only 8 remain. The 8 we have now. Okay? That's how our solar system formed. So, how old is the Earth? The Earth is actually 4.543 billion years old. I'll explain how we know that later. But, for now, I want you to think about that number. In life, we tend to think about numbers in terms of, like, change. Right? How many of you guys actually have change on you right now? Like, coins? A few. Okay. Not that often anymore. But we still think of it, right? The change, like the gas is like $3.89. A candy bar is $1.99, right? Okay. Lifetimes, tens. Hopefully 100. Hopefully you get there, right? Salaries, tens of thousands, hopefully hundreds of thousands someday, right? The US budget is actually in billions, but no one thinks twice about that anymore, right? The budget's approved in February, we're out of money by July, they argue about it, but we know that eventually they're gonna agree, all right, fine, give the government $4 billion more to operate through December, right? No one even thinks twice about that anymore. But I want us to think about how big a billion actually is. Okay? Let's do this. How many dots are on this sheet? By the way, I have said sheet right here. How many dots are on here? 100,000. 100,000. Do I hear it? Do I hear it once? Going once, going once, going once. Any others? Mia says 785. Okay. All right. We have a high end and a low end. Any other guesses? No one wants to take a middle ground between 785 and 100,000? Kate, what do you think? How many are on here? That's okay. Throw out a number. 10,000. Okay.
50,000.
50,000. Don't know. Okay. There are 4,000 dots on here. Okay. So each one of these sheets has 4,000 dots. How many sheets of paper would we need to reach 1 million dots? I know math. I'm sorry I'm making you do math. It's only 11:45. We don't get to say it's too early anymore. Now we get to say it's too close to lunch. I can't think. All right. How many 4,000s are in 1 million? It's okay to use a calculator. I'm like, I didn't say you couldn't. Divide 1 million by 4,000. What do you get? Huh? 250.
Oh, I put 2.
Oh, okay. There you go. Okay, yes, you get 250 sheets of paper like this for 1 million dots. Now, this is a ream of paper with 500 sheets. You would need about half this. But we are not talking about 1 million, we're talking about 1 billion. So how many sheets would we need for 1 billion dots? Cue brush. $250,000. It's 250 plus 3 more zeros. Because 1 million to 1 billion is just 3 more zeros, right? So you just three more zeros on the resultant of your previous equation. Okay? 250,000. Okay? Which is going to be 500 reams of paper, which are approximately 2 to 2.5 inches tall. So to reach 1 billion dots, that would be an 83-foot tower of paper, each of which has 4,000 dots. We're not talking about 1 billion, though, are we? We're talking about 4.5 billion. So for 4.5 billion dots, you need 2,250 reams, each of which has 500 sheets of paper, each of which has 4,000 dots on them, each of which represents 1 year of Earth's history, which would be a tower of paper 380 feet tall. That's how many years old our Earth is. I put it in perspective for you. It's a lot of years that have passed here. Show us some respect, right? Okay, let's beat this dead horse a little more. Who wants to stand up and go for a walk? We've been sitting down for a while, right? Well, I haven't. But let's go for a walk. We're going to go walk around the equator. Bring your Fitbits. How many steps would it take to reach 1 billion? Assuming the average human step length is about 2 feet, you would need to go around the equator 15 times to reach 1 billion steps. But again, it's not a billion, is it? It's 4.5 billion. That's 70 times around the equator. Who's ready to go? What if I offered extra credit? No takers? I was going to say, yeah. Not you guys would do anything for extra credit. Fly you? That defeats the whole purpose of the exercise. Okay. Now that we understand geologic time a little more, as far as the numbers are concerned, let's talk about the way that we organize the geologic time scale. Okay? You noticed before that it was organized into times and periods and all of that stuff. Let's talk about how and why we do that. So, if you have a piece of paper, please take it out or flip it over if it's another one you worked on. So it looks like this, 3 different sections. Okay? We're going to talk about the ways that we differentiate geologic time. Petrov is saying hello. When there's people in the classroom, he's like, hi guys, hi, I'm over here, hello. Little needy.
You don't take him out?
I do take him out sometimes. I don't mind taking him out. Now, he's just a little messy. He's like, he walks in his own poop, so it's like, sometimes he drags it around with him. And we can't put him on the table. He'd have to be on the floor, because he will crawl off the table. Let's do that after this exercise. Okay, so 3 boxes aligned just as so. Okay? Now, in the far left, I want you to write these words. We are not doing dates yet. Write these words, or, approximations of these words, okay? So at the bottom, you're going to write born, learn to walk, learn to ride a bike, start at grade school, so on and so forth. In this order, going up. Again, not the dates for these things, just these words. Go nuts. Okay, how we doing? Ready to move forward? Notice, by the way, the order that I did this. In our culture, we are used to reading top to bottom. But I started bottom. Right, now we're here. Sorry. Why?
That's how it's.
Because we're talking about geologic time, and geologic time, we follow the law of... What's that called? The law of?
Superposition.
Superposition! Oldest on the bottom. Bingo. Okay, so now let's move on to the middle column here. The actual dates associated with those things. These are my dates. Put your own dates. Don't steal my dates. It's rude. It's called identity theft. It's not a joke, Jen. Coming to say hi? Like, Daddy, hold me. Okay. We all there? For those of you doing the math, yes, I'm 32 years old. Okay. There's always someone who's like, wait, you're 32? I'm like, yeah, is that old or young? Why? Okay. Now draw a horizontal line between started grade school and learn to ride a bike. Above that line, we're going to call that period of your life the Schoolian, and below it, the Pre-Schoolian. Because up to this point, I hadn't started school yet. And above it I had. Now notice, I didn't include things like kindergarten on here. There's just no reference in my life in these three things for school. And above it there is. So I can divide my life into preschool and school time periods. This is exactly what we do with geologic time. Camera, what are you doing? You're killing me. Get over here. I wanna do it with, okay. Here we go. Hey, over here. What are you looking at? I'm right here. Dork. Right there. Thank you. Alright, so this is what we do with the geologic time scale. It is separated into sequential life events because, yes, we break apart the geologic time scale based on life. Biological events. The first reptile, the first plants, the first yada yada, okay? All of that stuff is what we use to break apart geologic time. Life events, numerical time, and then time intervals that we give names based on what happened in these life events. Okay? So let's look at this. Here we go. We have eons, eras, periods, and epochs. Those are the time intervals. Then we have millions of years ago. That's our numerical time. And our biological events, that's the sequential time. So like, look down here. Origin of multicelled organism. Boom. Line. Rise of all major animal groups. Boom. Line. First land plants. Boom. Line. That's how we differentiate geologic time. Okay? Just like we did with my life and your lives. Yes?
Where'd you get the two?
This one? He was a rescue from here in town. He's an Afghan species. This is in his native environment. Whoever was taking care of him before hadn't done a great job, which is why he has damage on the shell. He was getting in fights with local species, and he wasn't winning. So he was in a rough spot. This guy was like, hey, I don't want to have to take care of him anymore, so I took him. Almost, let's see, rescues. One rescue over there. The rest of them I bought or collected. Yeah. If there's an animal in a tough spot, like a reptile, I usually take it. But yeah, he's a long way from home. Fun fact, the first two vertebrate animals to ever go around the moon and come back were two Russian tortoises. Yeah. The Russians knew in the 60s that they were losing the space race to the Americans. The Americans were going to put men on the moon first, so they decided, hey, let's take what we can get. We're going to put two Russian tortoises in a spacecraft, and we're going to send the first animals around the moon. And they did. And those two Russian tortoises came back perfectly fine. Yeah. Two of these guys, first to the moon. Well, around the moon anyway. Okay. Questions about the geologic time scale? No? If I held you like a cheeseburger, would you be mad at me? What about this? Okay. I want to eat you. Don't crawl off the edge, please. You're going to crawl off the edge, like right up here. All right. You can do it. You can do it. There we go. Okay. So let's talk about the interior of the Earth. Okay, the Earth is separated into layers, like I mentioned before. Your core, your mantle. You're gonna off the edge. Give me a heart attack. Okay, you've got the core, you've got the mantle, and you've got the crust. Okay, so the crust is where we live, clearly. So we kind of know the most about that. I'm gonna put you in the sink for a minute. You can't get out. That's the sound of the green iguana's water turning on. Alright, yes, so the crust is where we live. We kind of know the most about that for obvious reasons, okay? The oldest material we have on the crust is 4.4 billion years old. That's the oldest material we've recovered here on Earth. 4.4 billion years old. But wait, Professor Hart, you told us Earth is how old? I just told you. We did a whole lecture on that. How old is it?
13.7.
Oh, that's the universe. Good memory though. What? 4.543 billion years old. But I just told you, just right here on this slide, I think nary 2 slides later, 4.4 billion years old is the oldest material we have on Earth. Did I lie to you?
Yeah.
You would think that of me? We've known each other for a whole 4 hours almost. 3 hours. It's not been 4 hours. Okay, 3 hours. And you think I would lie to you? I did not. No. Oldest material that we have that tells us how old the Earth is doesn't come from the Earth. It comes from somewhere else. Where might it come from? Space. Where? The moon. Yes! Our moon was formed when another one of those early planets hit Earth. We have a name for that planet. It's Theia. Early Earth and Theia collided with each other, and the result of that collision put a bunch of debris into space in our orbit, which eventually coalesced into our moon. The oldest material we have on the moon is 4.543 billion years old. Therefore, the Earth itself must be at least that old. Okay? Even though the oldest material on Earth isn't that old, the moon came from the Earth, so it must be that old, at least. It may even be older. When we get back to the moon and we start bringing back samples, oh, it's going to be so exciting. I'm so excited for that, right? We may even find out that the Earth is older. We'll see. We'll see. Okay, so let's start by talking about the crust. The crust is made out of mostly the lighter elements that make up the Earth, okay? It is mostly made out of oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. Those 8 elements make up 92% of the Earth's crust. Just those 8. 92%. The other 8%, everything else. Okay? This is most of it. Especially oxygen and silicon, those 2 things are going to come in a lot later in the course. Okay? The average thickness of the ocean crust is about 7 kilometers. The metric system is the language of science, by the way. When I remember, I have put the imperial system here. It's ironic that America is like one of the only countries that holds to the imperial measurement system, but here we are. The continental crust is about 35 kilometers thick, on average. Okay, so ocean crust thin, continental crust thick. The mantle is the thickest part of the Earth's interior, okay? We separate it into the upper mantle and the lower mantle. The upper mantle is really hot, technically hot enough to be melted, but is under so much pressure that it cannot melt. The lower mantle is also very hot, even hotter, but still cannot be in a melted state. It is solid, however, it is what I would call squishy. How can that be? How can you be solid and still squishy? Well, ask Plato. It's a solid. Dork. Knocked over my corn syrup. Okay. Yes, it is a squishy, still solid. Alright. You just peed everywhere. Alright. Good thing he's in the sink. But yeah, okay, so still solid, but conformable. Pressure pushes things in there around, okay? Like you can with Play-Doh. You can exert pressure on Play-Doh and it'll squish to whatever form you want. That's what's happening down there. Then we get to the core. You guys ever seen this movie? Oh, it's great. And by great, I mean awful. But you know what I'm talking about. Fantastic action, terrible science, as they all are. Actually, so every term I have a silly geology movie night with my classes for extra credit. So later on in the term, I'll send out a Google form for you all to vote on, and we'll choose a day that we can have a silly geology movie night. We can all get together, have some popcorn and drinks, and watch a silly movie, get some extra credit points out. Sound good? Awesome. Okay, this is one of the ones that is an option to watch. But in the core, there are two parts: your inner core and your outer core. Your outer core is the only liquid component of our planet. How many of you learned earlier in your education that under the crust, everything was melted? That is a perception of geology that we have known better since the 60s. And somehow it still pervades our education system at the lower levels. Elementary schools, middle schools, for some reason, a lot of them still teach that the earth is liquid under the crust. It's not. It's solid all the way down to the outer core. Okay? We've known better than that for 50, 60 years now. Okay? So, it is an iron-nickel alloy. So dense. 14 times denser than water. But still a liquid. Okay? Extremely hot. And extremely magnetic. Because it is very hot iron. The inner core is the same mixture of iron-nickel alloy, but again, so compressed at those depths that it is a solid. It is also extremely magnetic. So we have a magnetic ball inside of a magnetic iron liquid buffer. And get this, our inner core is rotating. Because it's inside of that liquid buffer, it's rotating at a different rate and direction than the rest of our planet. Our planet spins like so. Our inner core spins like so. How is that possible? Well, imagine if I had a bowl of water here and I put one of those golf balls inside that water. If I spin the outside of my bowl, is that ball going to spin? No, it's inside of that water. That water's not exerting any friction on it. Same thing's happening here. But this is the cool thing. Because we have a magnetic inner core rotating inside of a magnetic outer core, the interaction of those two magnetic bodies generates an enormous magnetic field. Think about the same one that is made by your fridge magnet that pulls it to your refrigerator. That times 1 billion, times 40,000 billion, right? It's huge, enough that it surrounds our entire planet in a magnetic field. And that's what protects us from like 98% of all of the cosmic and solar radiation that otherwise would burn our planet to a crisp. You know what a planet looks like that doesn't have a magnetic field? Mars. Mars had running water. Mars had glaciers, still has some. Did it have life? We don't know, but it 100% had running water. How do we know? We can see it from space, and we've even put rovers there. We have a rover there right now that's going along an ancient riverbed, collecting samples, looking for life, evidence of life, fossils. It had running water, it might have had life. Why doesn't it have running water anymore? Mars is a smaller planet. It's about 1/3 the size of Earth, which means that its inner core cooled off faster than Earth did. Once that outer core cooled off, it stopped the spinning of that inner core. No more magnetic field. No more magnetic field, no more protection from solar radiation. No more protection from solar radiation. The atmosphere got stripped away. The water evaporated in space. And here it is, a dead planet. And that awaits our future through 2 or 3 more billion years down the road. And then another billion or so years after that, our sun will go red giant and completely burn this planet away anyways. So, who cares? But yeah, that's what a planet without a magnetic field looks like. Okay. All right, Earth's continents are made out of those lighter elements like I talked about, right? The sodium, calcium, and oxygen, silicon, and things like that, okay? Which means that they are actually less dense than the mantle, which is why the continents are buoyant on top of the mantle. Both of them are solid state, but the buoyant thing is sitting on top of the denser thing. That's how physics works. Our ocean crust is made almost entirely out of mantle material, for reasons I will explain later, like next week, okay? Which means that it doesn't sit as high on top of the mantle. So, an example of this is density, by the way, density exercise. Density is a measure of mass per unit volume. So here I have 2 ships. These are actually the same ship, okay? These 2 ships have the same volume, occupy the same volume. This one, that volume is filled with shipping containers. It sits lower in the water than the one that has the same volume but less mass. More volume, consistent volume but more mass, more dense. That's what's happening here. Ocean crust, more dense. Continental crust, thicker but less dense. And so it sits higher in the mantle, which is why we are above the oceans. Okay? Where the ocean crust is under the ocean. This is a map of our current mountain belt system. Everything that's in yellow is younger than 100 million years old. Everything that's purple, that's older than 100 million, but still pretty old, like not active anymore, currently weathering, breaking down. Everything that's pink used to be purple, but is weathered down to surface level. And everything that is gray is what was pink, but is now covered by sedimentary rock, making it super old. So looking at this, tell me what you can interpret about the continents on our planet. Huh? I mean, yeah, most of it's old, but all of it is what? I mean, yes, technically. But all of it is made from what? Say it! I saw you mouth it. Mountains! He mouthed it. I was like, oh, yeah, okay. Everything, every continental mass on our planet was a mountain at one point or another. This is how continents are formed. They collide together. Continents collide together, make a mountain range. The two mountain ranges that are currently active where this is happening, the Circum-Pacific right here. Okay, that's our Circum-Pacific mountain range. And then right here, this is our Eurasian mountain range. Okay, Himalayas all the way up into the Alps and Apennines. Okay. All right, so the pink stuff we call those shields. That's basically the old mountain ranges that have weathered down to surface level. And then the platforms, that's the gray stuff. That's a shield that's now covered in sedimentary rock. Okay. All right, where our continents meet our oceans, we're almost done. We're coming up on the end. I told you this would be like the longest lecture, and I kept my promise. Okay. Where the continents meet the oceans, we call that a boundary, okay, or a margin, continental margin, okay, and that's broken up into a couple of different parts. We have our coastlines, which is solid ground. We have our continental shelf, which is continental material that's currently flooded by water because of the height of the ocean. Then we have a continental slope, which is just that gentle downgrade towards the deep ocean. Your continental rise, so now we are out literally into the ocean. Can you flip over? No. And then we have our basins, deep ocean basins. Okay, so it's this whole transition series that we go through. Deep ocean basins are made out of plains, which are these big, long, blue, deep, kind of boring expanses of not a whole lot going on. But then you can also have trenches. Trenches represent the deepest parts of the ocean. Trenches are where two plates are currently colliding with each other in the ocean, kind of making a divot at the bottom of the ocean, like this, where one is diving under the other. Those are the deepest parts of our ocean. You guys ever heard of the Mariana Trench? 11,000 meters deep. It's pretty deep. Okay. I once saw what was it? It was like a 5-gallon bucket that they took down to the bottom of the Marianas Trench, and they came back up, and the whole thing had been like squished, really small. Oh, and they took one cup of noodles, like the styrofoam cup of noodles. I've seen one of those that was taken down to the bottom of the Marianas Trench, and it came back up. It was the size of a thimble. It had compressed so much from the pressure. It's tiny. And then seamounts. Seamounts are what we call underwater volcanoes. If you think we have a lot of volcanoes at the surface, there's somewhere between 1 and 2 million of them under the water, which is why they still catch us by surprise. It's impossible to watch all of them when they erupt. Just why I think it was 2 years ago when Tonga had that seamount erupt a few miles off the coast, caught everyone off guard, covered the whole island with ash, flooded their city in a tsunami, their capital in a tsunami. No one saw that coming. It was one of millions of volcanoes that we just can't watch all of. Okay, so when two plates are splitting apart from each other in the water, we call that mid-ocean ridge. This is the mid-Atlantic ridge. It is currently splitting apart in the middle of the Atlantic Ocean, as the name implies, okay? So it is running right here between, this is Canada, here's Europe, okay? It is cutting right through Iceland. The nation of Iceland is sliced right in half by it. So I went to Iceland in 2017 because I wanted to have some fun with it. I went scuba diving in the crack that slices Iceland in half. So for a little bit of time, I was on no continent whatsoever. That was really fun. Then I followed that valley further along, and there's one place where the two halves come really close together, and I was able to touch both continents at the same time. Iceland is an amazing place. If you guys ever want to go anywhere in the world, you should go to Iceland. It's incredible. Okay. All right, let's finish by talking about plate tectonics. Plate tectonics, simply stated, is the theory that our planet's surface is broken up into a whole bunch of plates. Before, there was this thing called continental drift theory. In 1964 is when plate tectonics came around and continental drift was left behind. But continental drift basically is what I was talking about before, where all our continents are like bumper boats on an ocean of magma, and we're just floating around kind of bumping into each other and stuff. We now know that's not the case. We are solid plates moving around on top of solid mantle through a process called convection. Okay? So there are 7 major plates: North American, South American, Pacific, African, Eurasian, Australian, and Antarctic, and a ton of tiny little ones stuck between all the major ones. Okay? How does this happen? How do they move? Convection. Convection is the rise of heat and the fall of cold. Why? When you add heat to something, you're increasing its volume while maintaining the same mass. What does that do to its density? Volume increases, mass stays constant, density drops. If you are decreasing density, you are becoming more buoyant. So that means hot material will rise. It's true for water, it's true for oatmeal, it's true for air, it's true for everything. Yeah, I know. You ever seen a pot of oatmeal boil? You ever notice that stuff gets pushed up along the edges towards the middle and then falls back down? That's convection. It's getting pushed towards the middle where there isn't a hot wall, cooling off and falling back down towards the middle where it heats up and gets pushed up again. That's convection. That's what's happening in the mantle. The hot mantle material is rising, cooling off near the surface, and getting shoved aside by the newer, hotter material behind it. And that's creating drag at the bottom of our plates. And that's what pushes our plates around. So, when 2 plates are getting pushed into each other, we call that a convergent boundary. That's what's happening when 2 plates are getting pushed by 2 convection cells that are doing this. They're pushing the bottom of the 2 plates towards each other, making a new mountain range. Okay? Creating new continental material. When the opposite is true, when you have 2 convection cells doing this, moving in opposite directions, you get a divergent plate boundary. The 2 plates are moving away from each other. That's your mid-Atlantic ridge, where new material is getting pushed up to the surface, creating new ocean plate. Okay? Then you have another one called transform. Ready for this? It's like rub your head and pat your belly sort of stuff right here. Okay? You can try it if you want. It's fun. Okay? You get 2 convection cells that are moving in opposite directions parallel to each other. That creates a transform plate where the 2 plates are scraping next to each other like this. And this is what makes most of the stress required for earthquakes. That transform plate action right there, it's like a dance move, right? It's creating a lot of stress that when it releases, you make an earthquake at that boundary. Okay? That's what's going on along the coast of California. That's why there's so many earthquakes out there. Okay? Great. Next time we're talking about matter and minerals. What questions do you have for me about today's content? Okay, you can come out now. Lo and behold, you pooped. Clean up your shelf. Okay. Questions? Thoughts? Jokes? Should I leave you with a joke?
Yes.
Someone's been putting extra dirt in my garden. The plot thickens.
Can you go back to this?
Go back one slide, yes, sir. Alright, hope you had fun on your field trip, dude. Eat some mustard greens. Alright. Well, if there are no questions, then we can dismiss. I'll close the recording now. We will meet again on Thursday. We'll talk about matter and minerals. If you have any questions or concerns between now and then, please feel free to send me an email.